It's about time to get started. Y'all can go ahead and chat me your first and last name if you haven't done so already, just to keep track of who's attending and who's not. Again, this is no penalty on you for not attending in real time. You're not even technically required to watch at all. This is a little different than the other class in that it's a NO2, so it's a night class as opposed to a strictly online class. So there are different rules, but I don't hold my students even face to face to having to attend. If you can keep your grades up and not attend, or in y'all's case, if you can keep your grades up without actually watching my videos, then yeah, that's up to you. I do think that it's harder for you to pass. I think it's harder for you to definitely harder for you to get an A if you don't. So keep that in mind. But do try to watch them. And I just sent out an announcement. And I posted a link on the week 4 module as well. Last night I did a follow up to the chapter 3 lecture that I gave y'all in our last meeting. I basically just completed all the rest of the examples in chapter 3, and then I had a little time left, so I went into in chapter 4, not chapter 3. Then I had a little time left, and I went into chapter 5 and just covered a little bit about friction. But I'm going to be doing that over again tonight, so that part you could ignore. But I am asking you guys to watch that just because I can't justify using that much time. It literally took me basically 2 full 2 hour and 20-minute lectures to get through all those examples. Part of it's because I talk and I try to tell you stories and stuff like that, and I really should be more disciplined by not including all those stories. But there's sort of the stuff that hopefully keeps people occupied and entertained and paying attention. But anyways, I'm a work in progress. So, anybody have any questions before we get started? Okay. I want to say one thing too about the test. I just finished grading all of them today. I still have a couple people that haven't taken it, so I got to make new exams for them. But still, you don't want to discuss specifics with anybody about the test, at least for another week, just because I have a couple people that were out of the country and they could get a really unfair advantage. And the test was quote unquote somewhat easy in that the class average was really high compared to past class averages. But the thing I wanted to tell you guys is y'all need to take the instructions that I gave you in that test very seriously. Like I explained to you what you should do to try to get partial credit, and very few people use that. But the ones that did actually did a lot better and got a lot more partial credit. Not only that, I want you to pay close attention to the instructions within Respondus because there is very specific instructions about you panning the room and your workspace with the camera so that I can see everything within reachable distance, or what I call lungeable distance. So the video was supposed to show all the workspace that you're working, as well as down there by your feet and all that. And then while you're still doing that, you're supposed to show me all the stack of papers that you have on your desk. And then one by one, you're supposed to show me the front and back of each of those pages. Because then at the end of the test, you're given a time to submit your work, and you're going to have to show me those same pages again. If I see one of those pages are missing, that could be points off, or it might just be grounds to call it cheating. So just don't do that. So make sure you include all those. But the biggest thing is you need to take your time when you're showing me those photos, especially since a lot of people didn't follow the instructions of emailing me a PDF of those photos after you're done. So you're taking the photos with Respondus, and you don't have any way of storing those. But when you're done, you have 15 minutes to take a photograph of the front and back of all your work pages that you just finished showing me on the video. And then you're going to put them in like a Word document with like zero margins or maybe half-inch margins, and then save it as a PDF, and then email that to me. And that's supposed to be emailed within like 15 minutes after you submit your test. Some people didn't do that, and it cost them dearly because I couldn't read the versions of the worksheets that they showed me. And in other cases, I just couldn't give them partial credit because I could see it, but they didn't show me enough work. They didn't show me any of the equations they used. They just sort of threw numbers in there, and so be very careful and try to mind me regarding the instructions I give you on how best to work those. So that's the way the tests are going to work from here on out. With your class, it's going to be a little different because I have a lab instructor that handles y'all, whereas my online class, they're an online lab, so I handle them. But with a lab instructor, in the future, your face-to-face tests will be taken in the lab setting at the lab time per the lab instructor's directions. Okay, but still those same rules apply uh, regarding how you get partial credit. So if you start off writing the equation or equations plural as they appear on the equation sheet, when you start to solve it, just write the one or two or three equations you're going to use for that problem. If you find out afterwards you ended up not needing one, you just put a line through it or erase it, either one you can do. And then I want to see you taking those equations and plugging the values in with their units. I want to see you labeling the numbers that you were given and the numbers that were implied and the numbers that they were asked for. I want you to see you giving them the appropriate symbols so that I can see, oh, they know that x is a position. They know that x minus x zero is a displacement. They know that v is a velocity, a is an acceleration, f is a force, that sort of thing. So all of that with their units are necessary. And then I need to see your algebra and our calculus type work that you have to do to get the problem solved. Sometimes there's just no easy way of showing your work, and I try to point that out ahead of time. But like this time, I didn't with regards to one of the problems that wasn't that difficult. Again, I don't want to start with specifics because I've got people that haven't taken the test. Now, with that being said, I'm going to go ahead again and ask one more time. Does anybody have any questions before I get started? All right, it looks like we're all good. I'm going to go ahead and share my iPad screen to get us started, and hopefully that should pop up any second now. As I was saying, we did a good fraction of chapter four last meeting, but I stopped at that example with when we were asked to calculate the net force on that boat, and there were several good and very important examples after that. I did all those examples last night, and then even went into chapter five. That's the video I'm asking you to watch because that completes all the examples, and it does so fairly exhaustively and really focuses on you learning how to apply Newton's second law. So it's already on my YouTube channel, but I definitely want you guys to look at it at your earliest convenience. Again, I'm not saying you have to, but you would be crazy not to. Okay. All right. With that being said, we're going to go ahead and start into the next chapter, which is chapter five. And chapter five is called Using Newton's Laws, Friction, Circular Motion, and drag forces. So we're going to learn about friction. We're going to learn about the forces required to maintain, for instance, a circular path or a circular orbit. And we're going to learn about drag forces, which are the forces of air resistance that you might have thought when we covered chapter two and we're talking about free fall. We were sort of missing some key points because we were ignoring air resistance. Well, this will allow us to take into account air resistance as well, at least in the free fall version. So hopefully that'll help you as well. But that's where we're going from here. So with that in mind, I'm going to start off with giving you a little bit of description, and I've already shared my iPad screen, and there was actually something I forgot that I wanted to do before I share my iPad screen. Specifically, I wanted to show you guys an example to help you understand how friction works. So I'll just do it with the itty bitty window up in the corner over there. So if you can pay attention to this, basically here's my calculator, and my calculator has these little rubber nipples on here. Those are really helpful for this demonstration because plastic on any hard surface has almost no friction. But when you get a little bit of a grippy or sticky kind of rubber, then it gets a little bit more friction full. And that's what I'm wanting to point out to you guys. What I want you to do is imagine taking this or something else that's has a good deal of friction between it and your desktop. And I want you to lay it on that desktop and I want you to give it a little push. I mean, a light push to the left or the right, whatever's convenient for you. And what you'll see is it's not going to budge. Give it a little harder push and it still won't budge. Give it a little harder push still and it still won't budge. There's a good range of small forces that you can apply to it before it ever gets going. But the big thing that I want you to see is that eventually you get to a hard enough force that when you apply it, it breaks loose and starts moving. And not only that, it starts to sort of accelerate because immediately you feel that the friction force that was holding you from getting it moving is now a much smaller friction force. That's a key point that I want you to catch, okay? And so that's a demonstration I need you to do for your own knowledge and experience so you understand something very big about friction. In most cases, static friction is larger than kinetic friction, and static friction is a friction associated with two objects not moving with respect to each other. So, like me trying to get this calculator moving on my desktop when it's not moving, that it's involving static friction. But the instant it starts moving, at that point, it becomes kinetic friction. And those are the phrases we're going to use, and that's the kind of friction stuff that we want to talk about. So, to better understand that, I want you to consider a plot that I'm getting ready to make, and this is going to be a plot of the applied force, the force that I actually apply to, say, a calculator or a book on a desk or something like that, versus the actual friction force. So let me start off by drawing a coordinate system. So here's my coordinates, or my graph, if you will. And on this axis is going to be the friction force. Well, actually, on this axis will be the friction force. And I could actually do it either way, the way it works out. But the main thing is this will be my friction force in newtons. And over here is going to be FP, meaning F push or pull. And that also is going to be in newtons. And what you'll see is when you start pushing, for instance, when you apply zero force, you're going to get zero friction force. When you apply, let's say, 1.0 newtons of force, if that's smaller than a certain critical amount, then the friction force is going to be 1.0. If you apply 2.0 newtons, and that's still smaller than some critical value that we'll learn later, then out pops 2.0 newtons of friction force. And that continues. That's basically the way things behave, is the friction force static is just going to continue to be applied uh, as largely as it can up to some max value. So it's going to try to just cancel out the force. It's not a kind of a magical force that would make something move on its own. It only responds to an attempt to move one object with respect to the object it's sitting on. So when I apply a force of 1 Newton, it responds by supplying a friction force of 1 Newton the opposite way. If I apply a force of 2 Newtons, it responds by applying a force of 2 Newtons the opposite way. And that continues up until it gets to some critical value. And I wanted you to understand what that critical value is. It turns out that critical value is actually the static coefficient of friction, which we give the symbol mu. So there's the Greek letter mu with a subscript s because it's static. And that mu times the normal force gives us the max static friction force. Now, as I told you, if you're pushing that ruler or book or calculator across a desk, you put more and more force and nothing happens, more force and nothing happens, more force and nothing happens. Then all of a sudden you reach a force where it starts to move, and then you feel like it moves really easily and starting to accelerate because now the friction force has dropped down and gotten a lot weaker. So what shows you that happening would be this part of the graph right here, and then the graph continues off perfectly horizontal like this. So, what is going on up until this critical point is we're only dealing with static friction. And there, from that point on, we're only dealing with kinetic friction. And I want to point out what this value is. So I'm going to draw a little dotted line to show you what the height of this friction force is. And that friction force is mu kinetic times the normal force, like that. So from this point, actually, I should say from this point on, it's kinetic friction. And remember, kinetic, like kinesiology, like kinetic energy, that means motion. And from, let's say, this point to this point right here, this is static friction. Oops, I left off a T. That's not good. Static friction. So uh, you can see what it works, and the way we state this is because the friction force is not, again, it's not an animated or an intelligent force. It just sits there and does nothing basically. But what it does is continues to try to stop relative motion. It tries to take the two things that are touching each other and prevent them from moving as long as it can. So in doing so, it's never going to give you more than enough force because then it would be capable of making something move on its own, which would make it sort of in the realm of magic. And that's not what we study in physics. So the equations that actually account for this are the following. We have an equation for the static friction, and it's the static friction Fs is less than or equal to mu static times the normal force, which we've been talking about. And that less than or equal to just says, hey, the friction force is going to get as large as it can to try to stop motion. So it's always going to try to match your force up until that critical value, mu static times Fn, at which case it fails. Or at which point it fails. And then, of course, the kinetic friction kicks in which case you've got mu kinetic, or F kinetic is equal to mu kinetic times the normal force, like that. So that is the explanation of how uh, friction actually behaves. And if you look at table 5.1 in your textbook, which is page 118, you'll see that your author was kind enough to give us a table of values of coefficients of friction. And there's even, you'll learn from labs and problems that you work, you'll learn there's very easy ways to determine this. For instance, one way you can learn the static coefficient of friction is you can set something on a adjustable inclined plane, an inclined plane with a hinge on it, basically, and specifically mounted with a protractor so that the protractor can measure exactly what angle the inclined plane is tilted at. And what you can do is you can move the inclined plane up a little bit, and the inclined plane has to be made of one material that you're trying to find the coefficient of static friction for, and then the block that sits on top of it has to be made of the other material that you're trying to find the coefficient of static friction for. If you notice in the table, it'll say things like wood on wood, and then it'll give you the coefficients of static friction for that, because you have to have two different things to move relative to each other. They both can be made of the same thing, but you still would have to specify it as wood on wood. You wouldn't just say wood, right? Similarly, it's got ice on ice, metal on metal, steel on steel, rubber on dry concrete, rubber on wet concrete, rubber on other solid surfaces, Teflon on Teflon and air, Teflon on steel and air, so on and so forth. So all of those are different things. So what you would do is you take these two materials. Maybe you want wood on metal. You've got a wooden block sitting on a metal adjustable inclined plane, and you move it up, let's say a tenth of a degree, and then you give the inclined plane just a slight tap, and if the thing starts sliding down instantly, then you're pretty close to the critical point. You lower it back a little bit and you give it a tap, and if it still falls down, then you had gone too high. So you move it back a little bit more and it still goes down, then you probably had gone a little too high. But the main thing is you want to bring it up till it just barely starts to move. When you tap the actual inclined plane, it'll start to move and then sort of come to a stop by itself again. Once you've done that, you check the angle, and it turns out that the inverse tangent of that angle is approximately equal to the static coefficient of friction. So that's a way you could do it. Uh, Now, as I was telling you, in this table, it has, for instance, wood on wood, and you see the kinetic coefficient of friction for wood on wood is zero point 0.2. The static coefficient of friction for wood on wood is zero point 0.4. That's what I was telling you about, how the static friction force is usually larger than the kinetic friction force. Similarly, ice on ice is 0.03 kinetic, zero point 0.1 static. Metal on metal is zero point 0.07 kinetic and zero point 0.1 static. Steel on steel is about zero point 0.6 and zero point 0.7. Rubber on dry concrete actually makes no difference. It's zero point 0.8 and zero point 0.8, but rubber on wet concrete gives you about zero point 0.5 for kinetic and zero point 0.7 for static. Uh, that's a good selection of them, and that's enough for me to make my point. So now that we know how to actually go about calculating friction, and we're going to see examples of that, we also need to make some understanding, or I get some understanding of something in everyday life, in hopes that the concept here will help you in everyday life and apply, help you apply physics in a way that's helpful. So one of the things that you're probably used to is when the snow comes, we normally get a meteorologist or weatherman or weatherwoman or something will come on and warn us about the dangers of driving on ice, and they'll teach us how to turn into the skid. So I wanted to explain turning into the skid from a physics standpoint, and it's all about friction static being larger than friction kinetic. Okay. So first off, I got to do is I got to convince you that when a car is normally riding down the street, not skidding, not spinning out, not slamming on brakes and skidding that way, or not skidding as a result of making a turn too fast at too sharp an angle, but just regular driving, I need to convince you that at that point, the friction is static between the tire and the road. So the way I'm going to do that is with our relative velocity formula. Remember, the relative velocity formula said that the velocity of object A relative to object C was equal to the velocity of object A relative to something. I'm going to leave a blank there for a second, plus the velocity of object something, leaving a blank there on purpose, relative to object C. So the key point here was to understand that the left-hand side has two subscripts. The first subscript has to be the first subscript on the right-hand side. The last subscript on the left-hand side has to be the last subscript on the right-hand side. And the inner two subscripts have to be exactly the same. So I'll put B and B, but it could be E and E, or it could be Q and Q. It doesn't really matter. But that's our relative velocity formula. And remember, I even showed you how to deal with that. In special relativity, you just add that extra 1 plus VAC times VBC, or excuse me, VAB times VBC over C squared. That's all you have to do to make it relativistically correct. So now I want to have you imagine a tire on a car, and let's say the tire on the car is mounted on a car that's actually up on jacks like you'd see in a repair shop. So it's up on the lift, in other words, not really a jack, literally the lift. So the lift has those big arms that stick out and it holds up under the frame, and it's fairly secure. Some of the things I'm getting ready to talk about doing, you probably don't want to do in reality, but I'm going to pretend like imagine us getting in that car while it's on the lift, cranking it up, and turning, pushing the accelerator until the speedometer is reading 60 miles per hour. Again, not saying that's a good idea to do, not wanting anybody to give that a try, but that's what we're imagining. Now, the first thing I'm going to ask you, if I'm really going at, if I really have the speedometer in that car reading 60 miles per hour, how fast do you think the bottom of the tire is going relative to the car itself? Anybody? Again, the speedometer is saying 60 miles per hour. How fast do you think the bottom of one of the tires is going relative to the actual body of the car, or say the axle of the car? And checking the chat just to see if anybody answered. Not seeing a lot of answering. So if the car was really going, if the speedometer is really saying 60 miles per hour, that would suggest that the tires must be going backwards 60 miles per hour. When you're using this relative velocity formula, both the sitting still frame and the moving frame have to agree which direction is X and which direction is positive X specifically, as well as which direction is positive Y and which direction is positive Z, even though we normally only need one dimension at a time. So we're going to say in my diagram that the positive direction is to the right. And let's see if I can move this a little bit. Nope, I just make it bigger. That's not a good idea. Okay. So what we're saying right now is when the car is up on the lift, then the bottom of the tire right here has a velocity that's the velocity of the bottom with respect to the axle is equal to negative 60 miles per hour. Now, because of that, I suspect y'all know that the velocity of the top of the tire would also be 60 miles per hour relative to the car itself or relative to the axle. So notice I'm saying the relative the velocity of the bottom of the tire relative to the axle, VBA, is negative 60 miles per hour. Now, I'm also going to say the velocity of the top of the tire, which is velocity T with respect to A, is equal to positive 60 miles per hour. Okay. So that's something we know. Now that we've figured that out, what I would like to do is figure out what the velocity of the bottom of the tire is with respect to the road when the car is actually traveling at 60 miles per hour. Okay. So now we're imagining here's the car. It's not a pretty car, but it's a car. Okay. And now we're imagining that the car axle itself is traveling at, this is the velocity of the axle with respect to the road, is equal to positive 60 miles per hour. And if the axle's going 60 miles per hour, that means the front bumper's going 60 miles per hour. That means the driver's going 60 miles per hour. That means the windshield's going 60 miles per hour, all that good stuff. But what we want is the velocity of the bottom of the tire with respect to the road, which according to our rule should be the velocity of the bottom with respect to something plus the velocity of something with respect to the road. Well, I happen to have the velocity of the axle with respect to road, so it seems kind of reasonable for me to say the velocity of the bottom of the tire with respect to the axle plus the velocity of the axle with respect to the road. I can say that. Remember, you have the additional rule when you're using this that VIJ is equal to the negative of VJI. In other words, if you reverse the subscripts, all you have to do is change the sign to a negative. In other words, if it's a negative, change it to a positive. If it's a positive, change it to a negative. So in this case, I'm going to go ahead and compute what values we have. We already found that the velocity of the bottom of the tire with respect to the axle is negative 60 miles per hour. So I'm going to write in negative 60 mph, and we already know that the velocity of the axle with respect to the road is positive 60 miles per hour. So we see that when you add the two, you get negative 60, positive 60, you get 0 miles per hour. So that's your proof that there's no relative velocity between the bottom of the tire and the road itself when the car is just moving along without doing the skidding or the power braking or spinning out or something like that. Now, just for a neat little sidebar, let me show you how fast the top of the tire is going. So the top of the tire would be given by the velocity of the top as seen by the road, and that's supposed to be equal to the velocity of the top as seen by something plus the velocity of that same something as seen by the road. Again, I'm thinking A, so I'll put A in there. And in this case, the velocity of the top of the tire as seen by the road is 60 miles per hour, or excuse me, as seen by the axle, plus the velocity of the axle as seen by the road is plus 60 miles per hour. So that means the top of the tire is actually moving at 120 miles per hour. And that's a big deal. For instance, if you've seen tractors driving down the road before, you know that the tractor tire is literally like right beside the driver, and the top of it's going basically twice as fast as the tractor's going. So if the tractor's going 15 miles per hour, then the top of that tire is going 30 miles per hour relative to the ground, but only 30 miles per hour relative to the driver because he's going 30 miles per hour as well, or excuse me, 15 miles per hour as well. So the top of the tire relative to the driver would just be 15 miles per hour, but relative to the road would be 30 miles per hour. So now that we have that, we hopefully you're all convinced that the coefficient of friction that's relevant between the tire and the road in normal circumstances is the static coefficient of friction. Anybody have any questions on that? All right. So now I'm going to show you the anatomy of a skid. So what I'm going to do is I'm going to draw a curve that a car is taking. And there's the curve. Now, under normal circumstances, the car would just be represented by a little rectangle like this. And of course, the back wheels would be exactly parallel to the right side and the left side of the car. And that's what I'm trying to draw there. Now, since it's going around a curve, I'm going to try to draw the front tires turned just a little bit to the right. I'm not, and I almost have to over exaggerate a little bit, or I have to exaggerate a little bit just to show you that it's even angled. Okay. But the key point is that is what you got to do to make the car go in a curve, because if you kept the rear wheels parallel to the front wheels, or the front wheels parallel to the rear wheels, you just go straight and you'd run right off the road, and that's not that's not helpful, right? Well, as you're doing this, and of course your car is going this way, as you're doing this, if you hit a patch of ice, then what inevitably happens, mostly because the back end of a car is normally where the trunk and stuff like that is, whereas the front of the car is normally where the engine is. Because of that, the engine makes a larger normal force on the front tires than it does on the rear tires, and therefore you have a larger friction force on the front tires than you do on the rear tires, just because the friction force is proportional to the normal force. So inevitably, when you're riding around a curve like this, if you hit a piece of ice, the back end's going to tend to slip around like that. So I'm going to try to exaggerate the slipping around so that we can see how the tires would be turned, the front tires would be turned in the instant that skid starts to happen and your back end starts to slide out to the left. So I'm drawing it a little too big, and that's going to make me turn the steering wheel such that the front tires are probably turned more than physically real. I mean, there's a limit to how far you can turn your front tires in a car, but I might actually draw one that exceeds that. Okay. So if we think right now about the car after it skid a little bit, we would see that the angle of the car is no longer exactly parallel to the path we wanted to go. And in fact, the back tires are angled parallel to the left and right sides of the car. And the front tires are still turned sort of this way. And they're turned that way because that's the way they were turned before. So what has happened is the car has actually skidded from the position it was in before to the position it's in now. So, what the weatherman, weatherwoman, meteorologist, or whatever will tell you is to turn into the skid. And what they mean by that is if your tail end starts swinging to the left, then you want to turn your steering wheel to the left. Okay. So, if my tail end starts shooting off that way, I'm going to turn that way. That's what you're saying. So, the next course of action would be, and I'll draw another frame for this. These back wheels you normally don't have control over, even though for some period of time there was an idea of making cars where all four wheels turned, and there's probably still some that do that right now, but that went by the wayside pretty quickly. So if you actually followed instructions though, then you know the car is still trying to go this way, still trying to go this way, but turning into the skid would make the front wheels be parallel to that arrow there. In other words, if I turn my steering wheel to the left, like I suggested we were supposed to do, then they would be in that position. Now, because they're in that position, we can see that they have the ability to rotate exactly parallel to the direction the car is going. The back wheels are gone. You've got no ability whatsoever to recover that unless, like I said, it was a car that you could turn all four wheels. And even then, it was my understanding that the way they made the rear wheels turn, they only did it at certain speeds and they did it a different direction. And it was still a very minor turn. So the back wheels might not ever turn any more than this or this. And not only that, when you were doing it slow, they would turn like this to go to the right. But when you were going fast and you wanted to turn to the right, they would do like this. So it was a little weird thing like that. But by turning your wheels into the skid, i.e., by turning your steering wheel to the left when the back end was swinging out to the left, you've now aligned your tires so that they are pointing parallel to the path of travel. It's exactly what they said on the movie Cars when the guy was running on the dirt track and he kept sliding around like that and he would lose it and just run off the road or something like that. Well, when that back end comes around like that, if you turn your wheel to try to align it where your front tires are still going the same way the car is going, then you're turning into the skid and doing what you're wanting to do. And as they were telling him, you've got to turn right to go left. That was literally what they were saying, but they were right because if you don't turn right, you're going to lose complete traction and you're never going to be able to make that turn. But if you turn your wheels to the right, that can maintain your traction as you're skidding this way, going that way. And then when you finally slow down the skid, you can turn around the road a little bit. But that part turning has nothing to do with all this. It's all about that aligning your tires to the direction of travel. By doing that, what you've done is allowed the tires to regain static friction. Because if the tires can move in such a way that they turn the same direction the car is going, then there's no relative velocity between the bottom of the tire and the road surface. So that's why, in short, the answer for why do we turn into a skid in the snow, it's because static friction, which we've lost when we're skidding, is larger than kinetic friction, and the best way to restore that is to turn your wheels so that the front wheels are now aligned with the path of travel so that they can regain static friction. Now, as I told you, the front tires don't turn but for so far. So if you wait too long, you might be out of luck and you're just going to slide and possibly wreck. Hopefully you're okay and everything, but it's just going to happen. So anybody have any questions on that? All right. Now that I've had that discussed, we're going to go on to an example, and I'm specifically going to do example 5.1 from your textbook. So example 5.1, hopefully all of you have your book out, or at least your ebook up so you can see it. It says friction, static and kinetic. A 10-kilogram box rests on a horizontal floor. The coefficient of static friction is mu static equals 0.40, and the coefficient of kinetic friction is mu kinetic and equals 0.30. Determine the force of friction, F friction, acting on the box if a horizontal external applied force, FA, is exerted on it of a magnitude A, 0 newtons, 10, 100 newtons, or B, B, 10 newtons. I don't know where the 100 came from. C, 20 newtons. D, 38 newtons. And E, 40 newtons. So let me write down what we were told. We were told the mass is 10.0 kilograms. So it's already in the units that we want. The coefficient of static friction, mu sub s, is 0.40. The coefficient of kinetic friction, mu sub k, is 0.30. What we're asked to determine is the friction force in each case. And we're asked to determine the friction force in each case. And A is if the applied force F sub A is equal to 0 newtons. B is if the applied force F sub A is equal to 10 newtons. I'm going to assume they're all 3 sig figs, even though I'm writing just two. C, the applied force is 20 newtons. And D, the applied force is 38 newtons. And finally, E, the applied force is 40 newtons. Again, I want to pretend like everything's 3 sig figs, even though I'm only showing two, and in some cases even just one. So solution, F kinetic is equal to mu kinetic times the normal force. F static is equal to mu static, or excuse me, is less than or equal to mu static times the normal force. And that's pretty much all we need for right now. I have to draw the box now. So the box that we're talking about is probably like that box we've been doing in all the other examples. and this box has a mass of 10.0 kilograms. We have acting on it, of course, certain forces. This is the surface it's potentially sliding across. We have F applied going to the right, which I'm going to call a positive direction. So there's F applied. But we have other forces acting on it as well. So I'm going to go ahead and draw a free body diagram. And there's my X, positive X direction. There's my positive Y direction. There's my 10.0 kilograms. Acting on that is the weight, which acts in the negative y direction, and weight is, of course, equal to 9.8 times 10, so that's 98.0 newtons. We also have acting on it, of course, a normal force that acts in the positive y direction, so I'm using a green vector there. That normal force is F sub n. And we also have an applied force, which is pointing to the right and therefore is a positive force. That's the applied force, F sub A right there. And I guess I should put a vector on it because they are forces. But if you're just referring to the magnitude like I did with the W there, then it's okay to just write it as a W without the vector symbol over it. If I had the vector symbol over it, then it's not okay to write 98.0 newtons because that's not enough to specify a vector. All right, so now we can go about working that. And the whole question is, let me read again. A 10 kilogram box rests on a horizontal floor. The coefficient of static friction is 0.40 and the coefficient of kinetic friction is 0.30. Determine the force of friction acting on the box if a horizontal applied force, FA, is exerted on it of magnitude, and then I do the various magnitudes. So for starters, I got to do the summation of the forces in the y direction because I've got to determine the normal force. So the summation of forces in the y direction is equal to mass times acceleration in the y direction. And just like I kept doing all last night and the day before, specifically, when you're moving something along a horizontal surface, then the y coordinate's not changing. And the y coordinate not changing means that its velocity is zero. But the y coordinate not changing and still not changing and still not changing means the velocity is zero and it's not changing. So the acceleration is zero. Hence, I can go ahead and write acceleration is equal to zero. Now I can go ahead and say that the left-hand side is Fn, and that's positive because it's pointing up, plus the negative 98, which I'm just going to write minus 98.0 newtons, is equal to zero. So that tells us that our normal force is equal to 98.0 newtons. Now, that also tells us that F static maximum, remember the F static is less than or equal to mu static times the normal force. So the max it can be is mu static times the normal force, and it would help to know that. So I'm going to go ahead and compute that. What I need to do is compute 98 times zero point 0.4. And if my calculator comes on, it'll be a miracle. I don't know why it's not coming on. Oh, there it is. Okay. So I'm going to take F static max is mu static times Fn. So that's going to be the 0.40 times the 98. So zero point 0.4. Oops. You're just doing something weird. Hold on a second. I got to figure out where I'm at. Not there. Not there. Well, this is a neat thing to pop up right now. No, that's not good either. E activity. That's not good. Okay, so it looks like I'm going to switch to a different calculator because I don't know what happened to this one, and all of a sudden it's in a mode that I've never seen before. Let's see if this one's any better. So I'm going to say zero point 0.4 times 98, and that's 39.2 newtons. Okay. Now, the other thing is F kinetic is actually equal to mu kinetic times the normal force. So that's 0.30 times 39.2, or excuse me, times 98.0. So zero point 0.3 times 98 in that case gives me 29.4. So those are just key values I need to know. Now it's just a matter of working each of the parts. So for part A, F sub A is equal to 0 newtons. And what that means is the summation of the forces. Well, actually, you don't even need to do that. Uh, all they're asking for is the friction force. So if I apply a friction force, or excuse me, if I apply an applied force of 0, that means the table, the surface doesn't have to do anything to keep it from moving. So the friction force is just going to be 0. And it's technically going to be a static friction force of 0 newtons. And you can tell that that's pretty much the case on the last diagram because as you see here at 0 applied force, you got 0 friction, 0 applied force, 0 friction. So that's what happened there. Now we'll do part B. Part B, the applied force is supposed to equal 10 newtons. And what that means is 10 newtons is going to try to push this box to the right, but the friction force is static and it's going to supply as much of a force as it can up to a maximum value of 39.2. Currently, the maximum value or the value needed is only 10 newtons, so it's got enough to do that. So the friction is going to be static and it's going to be 10 newtons. And of course, it's technically in the opposite direction. So I might want to call it negative 10, but the main thing is that you understand that it's 10 newtons to the left. Okay. So that's our part B. For part C, F sub A is equal to 20 newtons. And that means that, again, it's less than the max static friction. So the static friction can match that. And that's what's going to happen. F static is going to be 20 newtons, and that also is going to be to the left. And part D, I'll put over here just because I can. So for part D, F applied is 39.2 newtons, or excuse me, is 38 newtons. And of course, that's still less than 39.2 newtons. So static friction is still capable of overcoming that. Therefore, the friction force is a static force, and it's actually equal to 38 newtons. And it's to the left. Finally, with part E, we see with part E, the force is 40 newtons, and that exceeds F max. FA is greater than F static max implies it will only experience kinetic friction. So the kinetic friction force in this case is only going to be 29.4 newtons to the left. Now, that means that the friction force is too small to keep it from moving. So, in fact, it's going to accelerate, and we can figure out exactly what that acceleration would be just by saying, and I'm going to do this. This is just extra, so I'll keep it in red. So, the summation of the forces in the x direction equals mass times acceleration in the x direction. Looking at the free body diagram, we see that we're going to have 40 newtons plus the negative of 29.4 newtons is equal to 10.0 kilograms times A, and that's our only acceleration, so I need not subscript it. What I end up getting, of course, is 40 minus 29.4, and that gives me 10.6. So 10.6, 10.6 newtons is equal to 10.0 kilograms times A. So A would be 10.6 divided by 10, which gives me 1.06 meters per second. So that's what would actually happen. It's just going to immediately default to kinetic friction once we've exceeded the static friction, and then the thing is going to actually start accelerating, which is again completely consistent with the example I told you to try to feel out yourself with your own calculator or book on your desktop. Anybody have any questions on that? All right. Conceptual example 452. It says a box against a wall. You can hold a box against a rough wall, figure 5.4, and prevent it from slipping down by pressing hard horizontally. How does the application of a horizontal force keep an object from moving vertically? So that's a kind of a neat philosophical conundrum, but once you think it through a little bit, you realize it's really not that big a deal. What we know is the friction force, which when the box is sitting still against the wall, the friction force would have to be static. And the maximum friction force you can have under static situations is mu static times the normal force. Well, the mu static is defined by whatever the box is made of and whatever the wall is made of. So you can't adjust that. But by pushing harder and harder on the wall's going to respond harder and harder with a larger normal force. Therefore, by pushing to the right, pushing the box against the wall to the right, the normal force, which points to the left, is going to get bigger and bigger. And by getting it bigger and bigger, the friction force, static friction force, is going to get bigger and bigger. Of course, the kinetic would too, but the static one is the one we're talking about because we're using it to keep it from moving. So that increased force to the right causes an increased normal force. That increased normal force causes an increased static friction force, and that increased static friction force only has to be big enough to sustain the weight mg. And if it's bigger than mg, then the box won't slide. If it's smaller than mg, the box will slide. So that's conceptual example 5.2. Anybody have any questions on that? All right, let's go to example 5.3 then. And I do have the chat window up in case anybody asks me that way, but you're certainly welcome to speak up. So this is example 5.3. And it says pulling against friction. A 10-kilogram box is being pulled along a horizontal surface by a force FP of 40.0 newtons applied at a 30-degree angle above horizontal. This is like example 411, except now there is friction, and we assume a coefficient of kinetic friction of 0.30. Calculate the acceleration. So I'm going to write down what we know. What we know is the mass is equal to 10.0 kilograms. What we also know is the pulling force FP is equal to 40.0 newtons. I'm putting everything in 3 sig figs, even though not everything's in 3 sig figs. This is applied at an angle theta equals 30.0 degrees, and there is a coefficient of kinetic friction, mu sub k is 0.300. Notice how I added an extra digit there. And what we'd like to do is calculate the acceleration. So A is equal to question mark. I'm going to draw the diagram, and then I'm going to draw a free body diagram. The diagram is the typical 10 kilogram box. We have acting on it a force that is not horizontal. In fact, it's raised at an angle of 30 degrees, and that force has a magnitude of 40.0 newtons. And then there's a coefficient of kinetic friction of 0.300, and that's going to result in a force that acts this way, which I should probably put in the red since it's definitely parallel to one of the axes I'm doing, but that's the friction force. And what we're going on here is we're assuming since the force was 40 newtons and we're talking about kinetic friction, I have to assume that this force is large enough to overcome the actual friction force, and that's why they only gave us kinetic friction. So now I'm going to go ahead and draw the free body diagram with the axes and all that good stuff. Okay, here's my positive x direction. There's my positive y direction. My mass right here is 10.0 kilograms. We have acting on it a force of 40.0 newtons at 30.0 degrees. We have also acting on it a weight is equal to 98.0 newtons. We also have acting on it a normal force, F normal, that we're going to have to determine. Additionally, we have a friction force that's trying to stop it from moving, and that is obviously pointing to the left. And that friction force is F kinetic. And now I have to be able to use that purple vector, I have to break it up into components parallel to the x-axis and parallel to the y-axis. Again, what we do is we imagine going from the tail of the vector to the head of the vector, from tail to head, but we do so by only going along parallel to the x-axis and parallel to the y-axis in either order. If I go parallel to the x-axis first, you can see I'm going to the right and then I'm going up. So the components are to the right and up, and that's both positive directions. So I'm going to go ahead and write this as this force right here is Fp sub x, and this force right here is Fp sub y. The sine of 30.0 degrees is opposite over hypotenuse, so that's Fpy over 40.0 newtons. Therefore, Fpy, which we already see as positive, so I'm going to force it by putting the sign on it. I'm now going to take and multiply 40 times, oops, there's an answer already in my calculator. 40 times, now I'm going to take the sine. Now I remember why I don't use this calculator. It's got the trig functions hidden. Oh, good. That's awesome. I love that for it. I love that uh, design. That's really, really helpful. Boy, let's see if I can get that other calculator on now. Mean menu. Okay. Ooh, got the other one working now. Thank God. That was terrible. Okay, so I'm taking 40 times the sine of 30, which should be 1/2, so that gives me 20.00 newtons. Similarly, the cosine of 30.0 degrees is root 3 over 2. And of course, I'm multiplying that by 40. So I'm going to say 40 times cosine 30. And that gives me 20 root 3, which is 34.64. Again, that one's also positive, so I'm forcing the sign right now. 34.64 newtons. So that's what our, whoa, Nelly, I skipped a step. Fp sub x is equal to positive 34.64 newtons. The step that I skipped was actually writing that this was adjacent over hypotenuse, and of course the adjacent side was Fpx, and the hypotenuse was 40.0 newtons. So now we have all that. Now it's just a matter of computing what the acceleration would be. So I need Newton's second law in the y direction to figure out the normal force. Then I use Newton's second law in the x direction to figure out the acceleration. So I continue as follows. The summation of the forces in the y direction equals mass times acceleration in the y direction, making the same argument I've made 1,000 times. Hopefully y'all know it by now. The acceleration in the y direction is 0. So this is going to give me F normal, which points up, plus Fpy, which we found was 20.0 newtons. That also points up, minus 98.0 newtons. That points down. That's why I did plus a negative, which is the same thing as minus. And all of that is equal to 0. Therefore, we see that the normal force is 98.0 newtons minus 20.0 newtons, which equals 78.0 newtons. So that's what our friction force, or excuse me, that's what our normal force is. Now I can use that to calculate our friction force. The friction force for kinetic is mu kinetic times the normal force. Remember, this one's kinetic. They told us it was kinetic, so we don't have to first, figure out whether it's smaller than some max quantity. The kinetic formula is just F kinetic equals mu kinetic times normal force. So in this case, I'm just going to take 0.300 and I'm going to multiply it by 78.00 newtons. Notice how that fact that we were pulling, not only were we pulling, but we were pulling upward a little bit. That upward pull made our normal force a little smaller. So that's why sometimes it's easier to pull things than it is to push. Like if you're pushing a big box, let's say a box with a dishwasher or something like that in it, if you're pushing it, your arms are pushing slightly down. Even if you really get strained, then you might push it horizontally, but you're still just pushing horizontally. You're not lifting up at all. Whereas if you're pulling it, there's a high probability that you're lifting up a little bit, and therefore you're reducing the normal force. And by reducing the normal force, you're reducing the friction. So 78 times zero point 0.3 gives us 23.40 newtons, and that's the actual friction force. Now that we have the friction force, we can go ahead and use Newton's second law for the x direction. The summation of forces in the x direction equals mass times acceleration in the x direction. In this case, we only have Fp sub x in the positive direction, and that Fp sub x is 34.64. So that's 34.64 newtons. Notice how I am using one extra sig fig for all these calculations. In the end, we'll go ahead and round it to the appropriate place, or at least I'll underline all the ones that aren't appropriate to use. But that's in the positive direction. In the negative direction is the kinetic friction. So I'd say plus or minus, but again, I'm just going to write it the easier way, which is minus 23.40 newtons, and that's equal to 10.0 kilograms times A, and of course that's the only acceleration we're talking about, so there really is no need to subscript it. So 34.64 minus 23.40 gives me 11.24 newtons is equal to 10.0 kilograms times A. So A is clearly 1.124 meters per second every second. So that's the acceleration of this block. And just as a reminder, I did this last night in that video, but I want to do it again now. Just because we're in chapter 3 and we're learning Newton's second law, that doesn't mean we're free from all that kinematics and projectile motion stuff. In fact, it's not uncommon for me to ask a question like this and say, assuming the box started at rest, how fast will it be going after 1 second? How fast will it be going after 2 seconds? Also, assuming the box started at rest, how far will it have traveled after 1 second? How far will it have traveled after 2 seconds? So with this in mind, I could say, okay, I know V is equal to V0 plus AT, but more importantly, I know that the acceleration being 1.124 meters per second every second says the velocity is going to change by 1.124 meters per second each second. So after 1 second, it'll be going 1.124 meters per second. After 2 seconds, it'll be going 2.248 meters per second. And after 3, it'd be going 3 times that, and so on and so forth. Additionally, as far as finding the distance goes, I know the equation that we'd want is 1/2 AT squared plus V0t plus x0 is equal to x final. That's the equation we're going to use. The fact that it started at rest means the V0t term is 0, and we can always set the x0 equal to 0, so we just have x is equal to 1/2 AT squared. Half of this 1.124 divided by 2, in other words, is 0.562 meters per second per second. So that's 1/2 A. Now that means after 1 second, it will be traveling. It will have traveled 0.5620 meters. After 2 seconds, it's going to have traveled 4 times as far, which is 2.248 meters. So again, that's just me rattling off how we could use our kinematic equations in this problem. And I don't expect you to be able to just jump and do that in your head necessarily, but I wanted you to know that that is fair game and that is the kind of follow-up questions that we can ask. I usually don't do that on a test strictly because I'm just trying to test one or two skills. And when I make a multi-part problem where you got all that stuff, if you get the first part wrong, it's really hard to give you a fair grade because there's some chance that you knew all the parts except the first part. And because you screwed up that first part, it was really hard for me to give you a decent grade on the subsequent parts. Someone asked, so you probably went over this, but how did you get the negative 98 again? Yeah, 9.8 meters per second times the 10 kilograms. Weight is equal to mass times gravitational acceleration. So the mass was a 10.0 kilograms. The G was a 9.8. If you multiply 10 times 9.8, you get 98. And then, of course, the fact that it was pointing down made it negative. Good question, Carmela. Anybody else have any questions? All right. So your book is then asking for conceptual example 5.4. I like to walk this out through, and it's sort of what I just explained to you about why sometimes it's easier to pull than to push. And it says conceptual example 5.4 to push or pull a sled. Your little sister wants a ride on her sled. If you are on flat snow, will he exert less force if you push her or pull her? See figures 5, 6a, and b. Assume the same angle theta in each case. So what they're showing here is a person pushing their daughter on a sled, and inevitably, because he's taller, he's pushing downward. That means the force is at a downward angle. Therefore, that force can be broken up into x and y components. The y component will be downward and therefore negative. The x component will be to the right and therefore positive. But that's the bare minimum. You have to have it going in the positive direction and the x direction to get it to move. But the fact that the y component is downward means that not only do you have the mg that the normal force has got to counteract, you also have the component of the force down that the father did in pushing. You've got that one pointing downward too. So instead of just having the child's weight and the sled's weight added together being equal to the normal force, it's the normal force is going to be the weight plus whatever that y component of the force was. So that's going to make the normal force larger. And since that normal force is larger, that's going to make the friction larger. And since that friction is larger, that means you're going to have to apply a larger force. So if you're on a flat snow, you will exert less. Will you exert less force if you push or pull her? Obviously, pushing her is going to make more force. If you reverse it and say, I'm pulling them now at that angle, theta, but it's upward. Now you can see the x component is still to the right, which is what we needed, but the y component is now up. So the normal force has a friend. It's got the normal force pointing up, but it's also got that component of force pointing up, and then that's combating the weight downward. So when you solve for the normal force, you get the weight minus that vertical component of force, and therefore that makes the normal force smaller, and then that makes the friction force smaller. Therefore, you need less force when you pull than you do when you push. Any questions on that one? All right, we're going to move to example 5.5 now, two boxes and a pulley. So two boxes and a pulley. It says in figure 5.7a, two boxes are connected by a cord running over a pulley. The coefficient of kinetic friction between box A and the table is 0.2. We ignore the mass of the cord and the pulley and any friction in the pulley, which means we can assume that the force applied to one end of the cord will have the same magnitude at the other end of the cord. We wish to find the acceleration of the system A, which will have the same magnitude for both boxes, assuming the cord doesn't stretch. As box B moves down, box A moves to the right. So that's the whole description. I'm going to go ahead and write down what they gave us. They told us that the coefficient of kinetic friction, mu sub k, is equal to 0.20. Uh, Mass A is, and I'm going to go ahead and make everything 3 sig figs. So mass A is going to be 5.00 kilograms, and mass B is going to be 2.00 kilograms. And what they're asking for is the acceleration A. Let me draw the pictures real quick so you'll have some idea what I'm talking about. So we have this box, which has a mass of 5.00 kilograms. It's attached to a rope that goes over a pulley, a massless, frictionless pulley at that. And then that pulley, of course, is mounted on the end of the table. And then the rope that's connected to the 5 kilogram mass is also connected to the mass MB, and that mass is 2.00 kilograms, like that. And what we want to know, like I said, is the acceleration. So to do this, I need to draw two free body diagrams. You guys are not necessarily familiar with this unless you happen to watch that video from last night or if you were there last night. But we did the Atwood machine, and that's the key thing when you're dealing. Well, not only did we do that, we did the Atwood machine, but we also did a train of three boxes, which there's an example in your optional videos already of that, so hopefully maybe you watch that one as well. But both of those are two of the main reasons I'm asking you to watch that video. There's also the Atwood machine, I mentioned that, but there's also a fuzzy dice problem that I think is critically important for you to watch as well, because they teach you different techniques of solving systems of equations, but they also teach you that you can treat Newton's second law, you can use that to treat a system, which could be both these masses and the string together, or you could use Newton's second law individually for mass A and individually for mass B. The disadvantage of treating the total A, B, and the string together is then you have no hopes of determining the tension in the string. And it gets really kind of dicey when you're doing something like this, trying to work it out. So I very rarely will group multiple things in together and use them as the mass on the right-hand side of Newton's second law. So let me draw the free body diagram real quick. One of the other things I taught them last night about this is when you do two things, especially two things like this, where the two bodies are connected by a string, then to avoid extra equations, it's best if you sort of align your coordinate system where if one moves in the positive direction and that automatically causes the other one to move a specific direction, then you make that specific direction the positive direction as well. So I'm picturing here that this 5 kilogram mass is going to move to the right, because I'm picturing here that the 2 kilogram mass is going to move down. So what I'm going to do is I'm going to treat the positive x direction to the right for the 5 kilogram mass, and I'm going to treat the positive x direction down for the 2 kilogram mass, and that'll keep me from having to have an additional equation relating the acceleration of the 5 kilogram box to the acceleration of the, excuse me, of the 2 kilogram box. Okay, so here's my mass. 5.00 kilograms. Sorry, I got hiccups. Now I've got a normal force acting on it. That's in the positive y direction, so that's F normal upward. I have a weight acting on it, and that's 40. That's W equals 49.0. Remember, 5 kilograms is half of 10 kilograms. Well, I knew 10 kilograms had a weight of 98 newtons, so obviously 5 kilograms has a mass of half, or excuse me, has a weight of half of that, which is 49 newtons. So that's how I did that math. We also have a tension, and the tension on the opposite sides of the pulley don't change. I talked a lot about that last night too. That's another reason that you're watching this video. But basically, if you imagine that pulley was very massive and had a lot of friction, then the tension in the string above the 2 kilogram mass would just be enough to slow down the 2 kilogram mass from falling at 9.8. And of course, that takes a little bit of force, but it's not a huge force. Whereas if you looked at the tension on the other side of the pulley, between the pulley and the 5 kilogram mass, that tension has to be big enough to keep the 2 kilogram mass from sliding downward, but it also has to be big enough to pull the 5 kilogram to the right. Not only that, the 2 kilogram one, the mass right above it, that has to have enough strength to not only drag keep the 2 kilogram mass from falling so rapidly, it's also got to turn that heavy frictionful pulley. So you'd expect the tension on the 2 kilogram to be slightly bigger than the tension on the 5 kilogram. So in absence of a heavy pulley and in absence of friction, you're going to get zero for those. So those two tensions should be the same. So I'm just going to call it T, not T5 and T2. This force is acting in the positive X direction. So I'm going to use a green vector for that. And that's the tension T. And of course, it's also subject to friction, which is the kinetic friction F sub k right there. So that's my free body diagram for the 5 kilogram mass. Now I'm going to draw my free body diagram for the 2 kilogram mass. Again, when the box moves to the right, the 2 kilogram box moves down. So I'm treating those as the same direction. Now I'm going to put my 2 kilogram mass right here. I know that if you were like in the box, you would say, okay, I know gravity's pulling down on me at, basically with a force of 19.6 newtons. And that's now a positive direction. That's the weight. And that weight is 2 times 9.8. And of course, 2 times 9.8 is 19.6. So that's 19.6 newtons. But if you were also in that box, you would say, oh, well, luckily we're not falling at G because that rope is slowing me down. And but for that reason, we know that the tension must be acting up. Now, this is kind of weird when you first see it, so I need you to sort of assume that Mr. Younger's telling you the truth and that you're going to have to do it this way every time. But as time goes by, it'll make more and more sense to you as you think it out that this has to be the way it is. Notice in the case of tension, you've got a rope pulling to the right in one case, and that's the tension. The other rope is pulling the opposite direction, and that's also the same tension. That's normal. Across two different free body diagrams, one object says the tension is pulling to the left, the other object will say it's pulling to the right. That's the norm. Okay, so keep that in mind. Now that we have that, we can go ahead and use the summation of forces in the y direction to determine the normal force. Once we have the normal force, we can then determine the kinetic friction. So I'm going to do that now. So the summation of the forces in the y direction equals mass times acceleration in the y direction. And again, this 5 kilogram box is going to be sliding horizontally so that y doesn't change. And y not changing means the velocity in the y direction is zero, and it's still going to be zero. So that means the acceleration in the y direction is also zero. So in this case, I get F normal, which is positive, minus 49.0 newtons is equal to zero. That means the normal force is equal to 49.0 newtons. Notice I added an extra digit because we always want to keep one extra digit for intermediate calculations. Now that I have that, I can say that friction kinetic is mu kinetic times the normal force. So I'm going to take that 49 and multiply it by zero point 0.2. And that gives me, of course, 9.800 newtons. So the actual friction force is 9.800 newtons, again, carrying one extra digit. Now that I have the normal force and the friction force, I don't need the normal force anymore. I just needed the friction force. But now I can go ahead and do the free body or the summation of forces in the x direction for the 5 kilogram mass, and then I do the same thing for the 2 kilogram mass. So this one was for the 5 kilogram. Now I do the summation. Ooh, that was terrible. Now I do the summation of the forces in the x direction for the 2 kilogram is equal to mass times acceleration for the 2 kilogram. Actually, no, let's start off with doing the 5. So this is going to be the 5 kilogram and the 5 kilogram. So the forces acting on the 5 kilogram are the the tension, which acts in the positive direction, minus the friction force, which is 9.800 newtons, and that's equal to the mass, which is 5.00 kilograms, times the acceleration. Now, here's the argument I made, and your author's just trying to tell you, hey, the acceleration of the two are the same, and maybe you don't necessarily understand that, but let me explain it this way. If I pull the 2 kilogram mass down 1 inch, unless the string stretches or unless the string was slack, both of which we're ignoring, we don't want to consider the string stretching and we don't want to consider cases in which the string is slack. But when we ignore those two cases, if I pull the 2 kilogram box down 1 inch, the 5 kilogram box will move to the right 1 inch. That means that their motion is the same. If I move the 2 kilogram box down 1 inch in 1 second, then I will move the 5 kilogram box to the right 1 inch in 1 second. That means the velocity of the 2 kilogram is the same as the velocity of the 5 kilogram, at least the speed. Obviously, they're different directions, but the main thing is the magnitude of the velocities are the same. Finally, if I move the 2 kilogram box by pulling it down 1 inch in 1 second and 2 inches in the second, then the 5 kilogram box is going to move to the right 1 inch in 1 second and 2 inches in the next second. So the acceleration of the 5 kilogram box is the same as the acceleration of the 2 kilogram box. So hopefully that's enough to settle it for you. And I'm going to call this equation one. It's really good practice to number your equations because when you're working with systems of equations, you know the fundamental rule of algebra says if you have three unknowns, you have to have three equations. If you have three unknowns and three equations and you inadvertently skip using one of them because of some algebraic mistake, you might be able to seemingly solve the system with only using two, but you know it's not possible. So by numbering the equations and then writing what you're doing with them, you can keep track of whether you use all the equations or not. So that's the reason I'm doing that. Now I'm going to take the summation of the forces in the x direction for the 2 kilogram box is equal to mass times acceleration for the 2 kilogram box, like this. In this case, I only have the W and the T. The W is positive. That's going to be 19.6 newtons. And the T is in the negative direction. So I'm going to say plus a negative T. And that's all equal to 2.00 kilograms times A. And I'm going to call that equation 2. Okay, so part of the thing that I wanted y'all to watch that video for was last night I showed you how to deal with equations like this in a way that you probably had learned in, pre-calculus algebra or even high school algebra 1, high school algebra 2. But the trick is if you have two of the unknowns and in one equation they have an exponent, they have a coefficient of like 5, and then the other equation they have a coefficient of like -5, then it's smart to add those two equations because the 5 times the unknown or times the variable plus the -5 times the variable eliminates that variable, and then you only have one unknown left and you can immediately solve. So that's what we're going to do here. We're going to add 1 and 2. And when I'm saying that, what I mean is I'm going to add the left side of equation 1 to the left side of equation 2, and I'm going to add the right side of equation 1 to the right side of equation 2, and I'm going to separate those additions by an equal symbol. I'm going to take an extra step because this is, for many of y'all, the first time you've seen me do it. So I'm going to say T minus 9.800 newtons plus, now I'm going to put the left-hand side of equation 2 in parentheses. That's just good practice because if you were, instead of adding, if you were actually subtracting or multiplying by a number and subtracting or just multiplying by a number and adding, then you got to remember that negative or that -2 or that +2 has to be distributed through all the terms. So it's good to go ahead and put a parenthesis around it. So that's why I'm putting this parenthesis 19.60 newtons minus T. And then the same thing for the right-hand side. I get 5.00 kilograms times A plus parentheses, square bracket, 2.00 kilograms times A. like that. Again, I just put the parentheses, the extra set of parentheses there, just as a good practice to keep you from accidentally forgetting to distribute a negative sign if it was subtracting, or distribute a multiplier if you were multiplying the equation by some number. Because you probably remember when you were solving systems of equations, sometime you would multiply one equation by 3 and the other equation by -2 and then add them. That's what that's for. Now, because I don't have any of those negatives, I can just go ahead and see that the t minus the t is going to cancel out, and I'm going to get 19.6 newtons minus 9.8 newtons, which is, of course, 9.80 newtons. And it's at 9.800 newtons. So that's the new left-hand side. That took care of the t's, and that also took care of these two. Now on the right hand side, again, I can drop those that square bracket, and you see I have 5 kilograms times A and 2 kilograms times A. So I might as well just factor out that A and say I have A times parentheses 5 plus 2 kilograms, close parentheses. So that would give me, oops, that would give me 7.00 kilograms times A for the right hand side. Now I can solve for A by dividing both sides by 7. 9.80 divided by 7 gives me 1.4, so I get A is equal to 1.400 meters per second. Remember, we're dividing a newton by a kilogram, and a newton is a kilogram meter per second squared. So if I divide out that kilogram, all I have is meter per second, which is exactly the unit that we want for acceleration. Any question on that? Now the problem didn't ask, but we can now. Now that we have A, we can plug that back into equation one or equation two and solve for t. I'm going to go ahead and do it just for extra, and I'm going to use equation one because it's already positive t on the left-hand side. So all I have to do is multiply the A times the 1.4. I mean the 5 times the 1.4 for A, and then add 9.8 to it. So from equation one, we've got t is equal to 9.800 newtons plus 5.00 kilograms times 1.400 meters per second. And of course, 5 times 1.4 would be 5 times 1 is 5. 5 times zero point 0.4 is 2. So that would be 7.0. So I get 9.800 newtons plus 7.00 newtons. Technically, I had another sig fig in there. So this is going to be, in fact, what, 16.8? 16.80 newtons is the actual tension in the rope. And that was, again, something that we weren't required to do, but I just wanted to show you that you could. Any questions on that? And your book calls that 17 newtons. Oh yeah, so they did the same thing in this example. I hadn't looked at it since a couple days ago, so I'd forgot they did that. All right, so we're gonna move on, and we're doing another problem that we handled last night, which was an inclined plane. So this is probably good practice for you as well. So I'm gonna go ahead and do example 5-6, and here it is. Example 5-6 says the skier. The skier in figure 5.8a descends a 30-degree slope. If the coefficient of friction is 0.10, what is her acceleration when she is in contact with the snow? So we're given that the angle of decline is theta equals 30 degrees, and they only give it two sig figs. I'm going to assume it's 3 just to make my life easier. We're going to say the coefficient of kinetic friction, mu sub k, is equal to 0.10 0. Again, I'm using an extra sig fig just for my own convenience. And they want to know what is her acceleration. A is equal to question mark. Notice they didn't give us her mass or anything. Okay. But we discussed that last night, so you'll see that it actually doesn't matter. But let me show you. There's a little bit of geometry here that I got to teach you in case you don't already know the geometry. So I'm going to work that out for you. But let me start by drawing a diagram and then a free body diagram. So the diagram is going to be basically an inclined plane like this. And the angle that this inclined plane makes with the diagonal is 30.0 degrees. Okay. Now, up on this, we're just going to treat her as if she's a little box, even though that doesn't seem reasonable at all, but we'll just pretend she's a little box just because we really have to treat everything right now as a point particle anyways. But there she is. Now, what we know is her weight is actually acting vertically downward, straight vertically downward. Okay. It turns out in most cases when you're working with inclined planes, it's better to use a X and Y axis system that is tilted parallel to the incline. I will teach you in this very chapter, in fact, that is a particular time where it's not good to use that, and this is not one of them. So just know that almost every time you need to use a tilted coordinate system. And because that coordinate system is going to be tilted, that means the vector that represents her weight is not going to be green or red. It's going to be just a random color because it's pointing straight down. It's not parallel to either axis. And in fact, it's just equal to m times g, where m is her mass. And I know I just drew that m in there super, super small, but that's the main thing. I just wanted to have it in there somewhere so you'd see that that's where I got the value from. So there's her mass. That means the weight is mg. Now I'm going to draw the free body diagram with the tilted coordinate system like this. And I got to still remember that the angle at which this is tilted is 30.0 degrees. And that's going to be what I call my x prime axis. And this is what I'm going to call my y prime axis. Now I'll draw the mass right here. That's just a mass m. I'll put that there. I have this vector already that's drawn straight downward, and that vector is W is equal to M times G. Now, I also have a normal force. Remember, the normal force is always perpendicular to the surface, so it's going to be parallel to that y-axis, and that's the positive direction. So my normal force for the skier is going to be this right here, F normal. Okay? Now, in addition to that, we're going to have a friction force, and that friction force is going to tend to slow her down. That means it's going to be in the negative y direction, or excuse me, the negative x direction, and there it is, F sub k. So again, we're going to use the summation of forces in the y prime direction to figure out what the normal force is, and then we're going to use the summation of forces in the x prime direction to figure out what the acceleration is. But before I can do any of that, I have to take this blue vector and break it down into components that are parallel to the x-axis and the y-axis. So to do that, I got to work a little geometry. So one way we can see this is the following. Notice that the inclined plane along the x-axis with the horizontal and with this blue vector makes a right triangle. Everybody see that's a right triangle? Because that's a right triangle, we know that this angle and this angle have to add to give you 90. That means that this angle right here is 90 degrees minus theta. Does everybody follow that? Anybody have a question on that? Okay. Now, the other thing we have to realize is that the angle between the negative y-axis and the positive x-axis is 90 degrees. So this too is a 90-degree angle. That's a 90-degree angle. If we, for a second, imagine this angle was called alpha, then because these two are 90, then we can reach the conclusion that alpha plus 90 degrees minus theta is equal to 90 degrees. That allows us to cancel out the 90 on both sides by subtracting 90 degrees from both sides. And then that tells us alpha minus theta is equal to 0. So we reach the conclusion that alpha is equal to theta. So now we know that the angle 30 degrees is the same angle as this one. So the theta that's down there at the inclined plane is the same as the angle between the vertical vector and the horizontal and the y negative axis. Okay. Because of that, we now have yet another triangle. That's a right triangle. And that right triangle can be used to figure out the, of course, negative y component and positive x component. So we can go ahead and draw that. The negative y component is going to be down here like this, and then the positive x component is going to be parallel to the x-axis like that. And hopefully you are now sufficiently experienced with the trig functions to know that the red side is going to be mg cosine theta, which would be mg cosine 30.0 degrees, and the green side is going to be mg sine 30.0 degrees. Now, this is never going away. We're going to be doing inclined planes probably till the last day of even the third semester of the course if you have to take the third semester somewhere. So this is, again, a thing that you've got to know. Okay, you've got to learn how to do this, and you got to do it every time. Now that we have that, now I can go ahead and write the summation of the forces in the y prime direction is equal to mass times acceleration in the y prime direction. Of course, I'm making the argument again that the skier is just sliding down the slope in contact with it. That means y prime is not changing at all. Y prime not changing means the velocity is not changing, or it means it has zero velocity. And then the fact that it still doesn't change means it has zero acceleration. So the acceleration in y direction is zero. And that gives us specifically that the normal force, which points up and therefore is positive, minus the mg cosine 30 degrees is equal to 0. And then therefore we know the normal force is mg cosine 30.0 degrees. And of course, cosine of 30 is square root of 3 over 2, which I think is like 0.866 or something. So it's 0.866 G, something like that. Now that we have the normal force, we can now compute the friction force. The kinetic friction is equal to the mu kinetic friction coefficient times Fn. And that, of course, is 0.100 times mg cosine 30.0 degrees. You could call it mg30 or mg theta if you wanted. It would look a little neater, but either way, that's good enough. Now we can take the summation of the forces in the x prime direction is equal to mass times acceleration in the x prime direction. And with this, we can see we've got two forces acting in the x prime direction. Notice one of them is the one that actually makes something go down an inclined plane. You know, if you think about gravity only pointing vertically, there's some question, unless you understand how vectors can be broken down, there's some question as to why does something fall down an incline? Clearly, the force is not pointing down the incline. Well, the force has a component that points down the incline, and that's the mg sine theta. So in this case, the positive is going to be mg sine 30.0 degrees minus the friction force, which is 0.100 mg cosine 30.0 degrees. and that's all equal to m times a. And of course, that's the only acceleration, so there's really no need to subscript the acceleration. What you also know is that now that we have Newton's second law written here, we can see that there's a common factor of m everywhere, so I can divide the left-hand side by m, and then, of course, whatever I do to one side, I have to do to the other. And of course, you also have to be very careful by dividing by variables. When you divide by a variable, if there's some chance that that variable could be zero, you could be doing something that gives you a faulty result. That's something you always got to keep in the back of your mind. But that's also true about multiplying by zero as well. When you multiply both sides of an equation by a variable, that's supposed to be allowed under the rules of algebra. But if that variable turns out to be zero, it could actually produce a an error or an erroneous. Having a hard time getting that word out. An erroneous result. All right, now that I've managed to calculate or divide out the m, I can see that the acceleration is going to be equal to a is equal to, in this case, we're going to write sine 30.0 degrees minus 0.100 times cosine of 30.0 degrees. That's a quantity we can actually calculate. It's not necessarily a fun quantity, uh, but there is a calculation we can do. So for instance, we know that the sine of 30 is 1/2, so that's 0.5000 carrying one extra digit. We know that the cosine of 30 is root 3 over 2, which I said was 0.8660. If I multiply that by zero point 0.1, then I get 0.08660, like that. So zero point 0.5. So if I do zero point 0.5 minus this, I get 0.4134 meters per second, or times g. I forgot that. Oops. By the way, the g went out here. I just factored out the g. That's how that works. I'll put the g out in front here. So this is 0.4134 times 9.80 meters per second per second. And that gives me an acceleration equal to 4.051 meters per second every second is equal to the acceleration A, and that's our answer. Anybody have any questions on that? And that one was not a sig fig. And actually, I added an extra sig fig. So your book is just calling this 4.1, or excuse me, 0.41, and yeah, 4.1, and I'm calling it 4.05. Any questions? So there's a really good example with a pulley, example 5-7, but I want you guys to go ahead and be able to get started. So I will do that one next time, or I might do it over the weekend and just send you a link for it. I need to get into the circular motion stuff. So to get you into the circular motion, I'm going to start off with a little exercise. We're going to create a vector valued function. Okay, there's a vector valued function, and the vector valued function is going to be r of t. So that's r as a function. Well, do I want it as time? Yes, I'll do r as a function of t. Now, what this is going to be is a capital R times cosine omega t times I hat plus r times the sine of omega t times j hat. Now, omega is going to be equal to 2 pi times a frequency. That's something we'll learn about later when we start studying circular motion and stuff like that. But we also know that that the frequency, the F that I'm using there. Notice this F is the same F I use for friction. It's just a cursive F that we use for functions. So in this case, this F is a frequency, and the frequency is related to the period of motion, as frequency is 1 over the period, or period is 1 over the frequency. So F is equal to frequency, and it's measured in cycles per second, which are also called hertz, which are also called CPS. So you might find some old government manuals that'll say CPS, and that's why it's not Child Protective Services, it's cycles per second. T is the period of rotation slash oscillation. And that would have units of like seconds or years or minutes or something like that. So you can see already that obviously cycles per second, cycles sort of not a measure, but it sort of is as well. The 2 pi is really just a conversion to radians. So when you're multiplying 2 pi times the cycles per second, what you're saying is each cycle is equal to 2 pi radians. So 2 pi f is converting that cycles per second to radians per second. Omega is called the angular frequency. Oops. I added an extra letter up in there. It's called the angular frequency or angular velocity, and that's measured in radians per second. Okay, so what is this vector valued function? Well, let me show you. This vector valued function we can represent on an axis like this, and this would be our x-axis, and this would be our y-axis. And let's assume R is about 4 blocks big. So if you consider t equals 0, then the cosine of 0, of course, is 1. So you get x is equal to r. And the sine of 0, of course, is 0. So you get the y component is equal to 0. So what this means is this vector right here is r, or excuse me, is r of 0. Okay. Now, if you consider r of, in this case, let's say t over 4, then of course omega is 2 pi f, and then t would be t over 4, but omega is also 2 pi over t. That's another way of writing it. So you'd see that that becomes 2 pi over 4. And then, of course, 2 pi over 4 is the same thing as pi over 2. And that's what happens here. We get a vector r of t over 4 is that. Then at r of t over 2, we get this vector. And then at r of t, or of 3t over 4, or yeah, 3t over 4, we get that vector. And what you see is that over time, this vector is a vector whose length is r, and it's just rotating around the axis like this. That's a vector valued function. Okay. And in fact, it makes a nice little circle, which I'll draw now, hopefully. Darn it, my dogs are barking. I hit my iPad a couple times and ended up keeping moving this thing in such a way that it turned out horribly, but oh, that looks pretty good now. Okay, so that's the actual path that we just drew there. And what we're picturing is this little R vector rotating around the origin in a counterclockwise direction. Now, if we take the derivative of this, remember R is a position vector. R is a position vector. So that V of t is equal to dr over dt. Okay? That means V of t. If I try to take the derivative of this, all I got to do is remember the I hats and j hats. They're for Cartesian coordinates, and they're just pure constants, so you don't have to do anything. If you're using something other than I hat, j hat, and k hat, or x hat, y hat, and z hat, then you actually have to do derivatives on them, but we're not going to do that, so don't worry. In this case, we're doing just the derivative of the part in front of the I. The r is a constant, the omega is a constant, and what we see is the derivative of cosine is negative sine. But then we got to use the chain rule to take the derivative of the omega t. So we're going to get negative omega r sine omega t I hat, and that is our actual, actually I just made a mess of it. That is our actual x component is negative omega r sine omega t I hat, and then the derivative of sine is cosine, but we got to do the chain rule on that one too, so I get positive omega r cosine omega t. J hat. Now, this might seem a little weird, but one thing you can do is you can go ahead and calculate the magnitude of this v of t. And you notice it's just a vector, so the Pythagorean theorem works. Even if it was three dimensions, the sum of the three squares would give you the magnitude as well. But this is just two of them, so we can do it this way. So that's going to be the square root of omega squared r squared sine squared omega t plus omega squared r squared cosine squared omega t. And you can see there's a common factor of omega squared r squared in there. Well, once I draw the exponent on the r, there will be. So I can factor that out, and of course I just get omega r. But then what I would have left is omega r times the square root of sine squared plus cosine squared, but the sine squared plus cosine squared is just equal to 1, so it's omega r times the square root of 1, just which equals just omega r. If you took the magnitude of r, you'd get an r, by the way. So, for instance, r of t would equal the square root of r squared cosine squared omega t plus r squared sine squared omega t, which equals the square root of r squared times sine squared omega t plus cosine squared omega t. And now you can see that this quantity is just 1. That's the same thing I used above. So the magnitude of r of t is just plain r. So the vector is always going to have the same length r. The velocity vector is always going to have the same length omega times r. Now, in addition to that, we have an acceleration, and the acceleration as a function of time in magnitude is equal to, well, let's start off with not the magnitude. Let's just start off with the vector itself. So a of t is equal to dv over dt. I've got the v up there. The derivative of negative omega r sine omega t is essentially the derivative of sine. The derivative of sine is cosine, so I'm going to get negative, and then I got to take the derivative of omega t. So now I have negative omega squared r cosine omega t I hat. And then the next one is the derivative of cosine omega t, which is negative sine, and then times omega. So in this case, I'm going to get minus omega squared r sine omega t. And that's in the j hat direction. And now we can calculate the magnitude of a of t. And by doing that, what we see is we basically just get omega squared r. But we might realize that that is omega r times r. And of course, omega r is v. So we could say this is v times r. R specifically R times V, whichever one you want. The main thing is we find that we have an acceleration that is a constant. V equals R omega. No, that's not the one I want to do. Let's do it this way instead. This actually works. Omega R was in fact V. We did find that. But what I could do is I could say this is omega squared R squared. So I could call this omega R quantity squared divided by r, you'd see that that does give the original result, because if I squared omega times r, it would be omega squared times r squared. And then if I divided that r out, it'd be omega squared times r, which is what I had originally. But that omega times r is just v, so that's v squared over r. So that is what we call the centripetal acceleration. So that's our centripetal acceleration formula. But in doing it, we now have a formula for exactly what kind of acceleration we have to make something going in a circle. For something to go in a circle, it has to have an acceleration either given by omega squared r or v squared over r. So, for instance, if you wanted to, calculate the orbit of the Earth, or excuse me, the orbit of the Moon around the Earth, then what you would say is you'd say, okay, the force of gravity is the only force acting on the Earth, so that's the left-hand side of Newton's second law: summation of forces equals mass times acceleration. But then the right-hand side is going to be the mass of the Moon times v squared over r, where v is the velocity of the moon at any instant. And you can go ahead and solve for that. And actually, what you'd end up getting is Kepler's third law of planetary motion. So that's the big formula. You also notice that this acceleration vector is going to point radially inward, because notice if you look at the v, the only difference for the v is basically what you had for the x component of the position is now the negative of the y component for velocity. So what that means is our velocity would be v of, in this case, 0. And right here, it would be v of t over 4. And right here, and I'm trying to draw all these the same size because that's what they're supposed to be. This is v of t over 2. And this one would be v of 3t over 4. And then if you look at the acceleration vector, notice that is exactly the same as the r vector, except it's multiplied by a negative omega squared r. So now what we can also see is that there is an acceleration vector that points the opposite direction of r. So that's a of 0 points in, a of t over 4 points in, a of t over 2 points in, and a of 3t over 4 points in. So now we've figured out basically the basics of circular motion. We can represent it by this r vector given as r cosine omega t I hat plus r sine omega t j hat. And we then see the velocity vector is going to be perpendicular to the r vector at each position, and it's going to be in the same direction that the thing's going. And then the acceleration vector is going to be anti-parallel to the r vector. So we know that the acceleration must be towards the center of the circle, and the velocity is always going to be tangential to the circle. That's what we needed to understand to solve circular motion problems. So let me just give you one example real quick now that we have that formula that's so critical. And the main formula is this one, by the way. A centripetal is equal to v squared over r. That was the purpose of all that. And this is an exercise you can do for extra credit. I'll try to remember to put it in your module, but it is an exercise you can do for extra credit. And I highly recommend it. It'll get you, used to working with vector calculus and that sort of thing. So your book goes through a neat derivation that doesn't really need calculus too terribly much, but they get the same result we do. I like my result better. Uh, let's see this example 5.8. Example 5.8, acceleration of a revolving ball. A 150-gram ball at the end of a string is revolving uniformly in a horizontal circle of radius 0.600 meters, as in figure 5.10 or 5.12. The ball makes 2.00 revolutions in a second. What is its centripetal acceleration? So we have a m is equal to 150 grams. Of course, we need that in kilograms, so that's going to be 0.150 kilograms. We know that it has a radius. The orbital radius of it is 0.600 meters, and we know that the ball completes 2 revolutions in a second. And what that's telling us, revolutions is another word for cycle. So what that's telling us is the frequency is 2.00 cycles per second, are 2.00 hertz, which is abbreviated capital H, lowercase z. And what they want to know is AC, the centripetal acceleration, is question mark. So I gave you the litany of all the things that went into this omega. I said omega was 2 pi f. I said f is 1 over t and stuff like that. And we know that AC is equal to v squared over r. And we also found that v is equal to r times omega, and a is equal, we'll learn that later, but A turned out to be equal to omega squared R, like that as well. So we can figure out it from various ways. This could be, we could use omega squared R, or we could use V squared over R. We mostly use V squared over R in physics, so I want to show you how we're going to do that. What we know is it's going around a circle, which is a distance given by the circumference. So we could say that V is equal to 2 pi times the radius divided by the period. That's one way of calculating it, but we don't know the period. We were actually given the frequency, but we do know the frequency, or the period is 1 over the frequency. So that's going to be 1 divided by 2.00 hertz, which equals 0.500 seconds. So now we can say V is equal to 2 times pi times 0.600 meters divided by the period, which is 0.500 seconds. And if I do this math, it's 2 times 3.14159 times zero point 0.6, and then we're going to divide that by 0.5, and that gives me 7.540 meters per second is the velocity that the object is going. And now the centripetal acceleration is 7.540 meters per second divided by 0.600 meters, and that gives me 12.57 meters per second per second. That means in order for this thing to be going in a circle, it must have an acceleration equal to about 12.6 meters per second every second. And that's radially pointed inwards. In other words, it's perpendicular to its velocity and points towards the center of rotation of the motion. Anybody have any questions on that?
Should the numerator of velocity be squared?
Uh, yes. If you're talking about the numerator of the velocity in the AC, you mean?
Yeah. Yeah, the
Yeah.
7.54.
Oh, yes. Thank you. Yeah, that's just a boneheaded mistake on my behalf. Thank you for that. I don't know what I was thinking, but yeah, that means the 12.57 is not right. Thank you for catching me on that. That's excellent. So seven, oops, I got to get back to my right color. So seven, thank you for that. I can't believe I did that. That's terrible. That's meters per second. And yes, it has to be squared. And notice I was looking at it and it was giving me meters squared or meters per second divided by meters. And I said, oh, yeah, that's meters per second squared. I literally checked my units and thought, yeah, I did that right. I did not do that right. 7.54 squared. Darn it. 7.54 squared gives me 56.85 meters squared per second squared. And now I'm going to divide that by zero point 0.6. And yeah, that gives a lot different figure. That gives a figure that's equal to 94.75. Ooh, that's a lot bigger. Meters per second every second is the centripetal acceleration. Notice the word I'm saying there, that's centripetal, which the Latin means center seeking or center traveling to. So it's centripetal, not centrifugal. Fugal is actually, there's no such thing as a real centrifugal force. That's just a common misunderstanding of something about physics that we'll learn. But the main thing is it's centripetal acceleration, and that is the acceleration that you have to move to towards the center to keep a circular orbit. Anybody have any questions on that? All right. Well, we only got about 4 minutes left, so I really don't have enough time to do much more, but I've at least given you one example of a centripetal acceleration. The other thing I'll tell you, since I have 4 minutes left, the drag force, F drag, has two different flavors. It's either directly proportional to the velocity or the drag force is directly proportional to the velocity squared. That's the two different scenarios. Our book, when we go to study it in this chapter, we're going to use the first one. So we're going to say the force of drag, in other words, the air resistance force, is equal to some constant times velocity. F equals B times V. That's the version that we're going to use. In reality, though, if you're dealing with really viscous fluids or you're driving really, really fast, for instance, then the V squared is a better term. I will tell you that the B has something to do with the viscosity of the fluid you're going through. So, for instance, it'd be a much bigger value if you're going through seawater, and if you're going through, for instance, syrup like maple syrup instead of seawater, it'd be even bigger value of B. But there's also another value in that B. The other value is the cross-sectional area. So, for instance, if I if I jumped out of an aircraft and it spread my arms and legs as wide as possible and tried to belly flop onto the ground or the ocean or whatever, the area that you see, in other words, the area that would take to just paint my front half, that's your cross-sectional area. It's the area perpendicular to your travel. That B is also includes that area in there. And if instead I decided to dive head first, then you would get a shape that looks something like this, where you're seeing the tops of my shoulders and my head, and this area right here would be the cross-sectional area if I was diving head first, and therefore that would be a lot smaller area, and therefore my drag forces would be a lot smaller. So those are two of the things that it acts on. I think if I remember correctly, the law that tells you about drag is called Poiseuille's equation, Piuesse or something. Uh, and I probably did a really bad job of spelling that, but I think if I remember correctly, I think that's the equation that they use for drag force. It's not my area of expertise. Your book doesn't even cover it to my knowledge. It might be listed in one of the problems in this chapter, or maybe even in a later chapter, but that's basically what we're using. So now you should be able to at least attempt all of the types of problems we have. The time is up, you guys. If you haven't chatted me your first and last name, please do so before you leave. But you're free to go, and I'll wait here for the last person to leave in case anybody has any questions. Thanks for coming, everyone. Paloma or Cameron, do y'all have any questions? All right, well, I guess that's it. Y'all have a good one.